Welcome everyone. In this video, what we're going to take a look at is we're going to focus on calling conventions in our compiled programs, predominantly C programs. So you see here we have 3 example C programs, and each one of these is going to use a different calling convention: standard call, the C declaration, and fast call. So our focus will be on understanding really what the difference between those calling conventions is and how that impacts when we're trying to reverse engineer a program and understand the arguments that are actually passed to that function. So that's really our main purpose here. So let's start by looking at these sample programs. Now, before we get into the sample programs, you will be able to find these programs on my GitHub. If you just search for my name, J Strosch, J-S-T-R-O-S-C-H, I have a repository called Learning Reverse Engineering, and there will be a folder here by the time I get this video uploaded that says calling conventions. So you'll be able to find these simple programs there. Of course, you can see them here in the demonstration. They're pretty easy to just to create on your own. So with each one of these programs, then it's really the same thing in each program. We have a main function. Inside of that main function, we have a declaration of one local variable, integer a, and that local variable is assigned the return value of the call to function demo, in which we pass 4 arguments, 1, 2, 3, and 4 in that order. Now, with each function call, right, you'll see that the demo function is defined as the same in each one of these programs. The only thing that differs is that in between defining the return type and the name of the function, we can actually define the calling convention that we want to use. So with this first program here is defined as standard call. Those are 2 underscores that prefix that calling convention name. We then have __ C decl or C declaration. And then finally, we have __ and fast call. Now, you'll see the difference between these 3 calling conventions here in just a moment, but the main difference is that with the C declaration, arguments and all of these calling conventions push the arguments onto the stack from the last argument to the first. So you'll see that when we get into reversing these programs. You'll see push 4, push 3, push 2, and then finally push 1. What changes then, so what C declaration will do is it's saying that the caller is responsible for stack cleanup. So if you recall, the stack is a region of memory, a virtual memory, that is used within the program for local variables and arguments and the control flow of the program. When you use the call instruction, for example, the call instruction will push the next address onto the stack so that when the function unwinds or the function returns, it knows where to go, the instruction after where it was called. So this declaration, this calling convention, then C declaration, requires that the caller has to clean up the stack. So for every push, and a push is going to, on a 32-bit system, push in 4-byte increments, we have to clean the stack up after the call. So typically you'll see an add to ESP an equal amount per the number of pushes. Now, keep in mind also that as the stack grows, we tend to think of it as a structure that grows from shorter to taller. But in actuality, it actually grows from higher addresses to lower. That means that when we push onto the stack, we're subtracting from ESP in order to make the stack grow. When we want to then shrink the stack or clear the stack, in this case for these arguments, then we want to add to ESP. So you'll see that here in just a moment. Now, standard call, same thing. Arguments are pushed onto the stack from right to left. So you'll see push 4, push 3, push 2, push 1. But the callee is responsible for cleanup. So instead of seeing a push, a call, and then maybe an add ESP, with this calling convention, you'll see the pushes, the call, and then inside of the function, you'll see a return or a ret, and then a value that represents the number of bytes that need to be cleaned off the stack when that function returns. So the function that was called is responsible for stack cleanup. Finally, with fast call, what we have is an attempt to use registers as essentially a performance gain in terms of passing the arguments. So the last 2 arguments, well, actually the first 2 arguments will be moved into registers, ECX and EDX, and then the remaining arguments are just pushed onto the stack. So what you'll see here in a moment is that we'll have a push 4, a push 3, and then we'll see a move into a register for 2 and a move into a register for 1. Okay, in order to compile these, as you've seen in many of my previous videos, we just need to use the developer command prompt. I just installed the community edition of Visual Studio in order to get this, and then we use CL and the name of our source program. So CL cdecl.c, CL fastcall.c and cl standardcall.c. So if you keep the original names that these were committed to that GitHub repository. Now we have a series of executables that we can reverse engineer. The next step is to open up Ghidra. Now, I've gone through this in many videos, so I'll just go through this a little bit quicker here. If you're not as familiar with getting Ghidra up and running, you'll want to refer to some of the previous videos here in this reverse engineering series. So we load Ghidra. We go ahead, create a new project. I called this calling conventions. We can then drag and drop or add, whichever way you prefer, our executables. And once we have those executables loaded, then we can drag those all at once or one at a time onto the code browser, which is this little drag in here. This will open up the main code browser tool. This is the main platform for doing our reverse engineering. And what you'll need to do then next is Ghidra will prompt you for analysis. You'll go ahead and analyze the program. And then after that, you're ready to begin doing your reverse engineering. Now, one thing you'll notice, especially if this is something that is maybe somewhat new to you, I'm going to back up a little bit here. What you'll notice is that when Ghidra is done analyzing the program, it leaves you at the beginning of the program, the actual beginning, not the beginning function, not the entry point, but the first few bytes of the PE, the original program, the PE file, the executable. So you have to navigate to main. You can do that since we use Microsoft Compiler. I find this is a pretty effective technique in opening the functions, scrolling down to the entry. So we'll click on the entry point. Now you'll see that in the listing view here, this is our disassembly. Off to the right-hand side here, I have the decompiler view. There's quite a bit of code here. This is all code that was added by the compiler. So we're looking for main. We're looking for the beginning of the code that we wrote to study here, and we don't want to get lost in any of this code. So we scroll down about 3/5 of the way. I know this to be the function, but what you can confirm by looking at the listing view is that you have a call preceded by 3 pushes, and that will be argv, environment p, and argc. I do believe I have those defined. Oh, no, I didn't define those in main, but typically those are defined in main, argc, argv, and environment p. But as you can see there, you don't have to, but that's what those 3 pushes represent. Now we can double click on that function, and we are now in main. And now is, of course, a good time to rename this, just in case you were, so you don't forget. You can right click here and go to edit function, and we'll just go ahead and say that this is indeed main. Okay, that way we won't forget. Now we're looking at both the decompiled results, which looks very similar to what we just looked at. Here's our call to our function. We have the 4 arguments, 1, 2, 3, 4, just as we'd expect it, and then the program terminates. It returns 0 because we didn't define another return value from main. If you look at the disassembly, you'll see that there's a little bit more going on here. We have our push EBP, move EBP, ESP. This is what we typically use, or you will see for the beginning of the creation of a stack frame. So the stack frame then is the region of memory that each function will use for its local variables, for arguments and other things. So the stack frame then is the region of memory for each function. It will include things like some metadata type stuff, old values of EBP. It'll have the return address. It'll also have space for local variables and then for arguments. So each function will most times then create a stack frame for its use. So here we have push EBP. That is, we are now storing the previous value of EBP onto the stack. EBP is typically the register that is used to create the base of the stack frame. We then move into EBP ESP. So this is where that basing occurs. Now in EBP is the current top of the stack because we just pushed onto the stack EBP. Now you'll see things like push ECX, and the compiler can sometimes opt to actually do other instructions. So instead of subtracting from ESP, say a sub ESP4, in order to get space for local variables, it just opted for a push. So push ECX. So ECX actually has no real value here other than it is moving our stack pointer 4 bytes. And the reason that it's doing that, if you go back to the original program, you'll see that I did in fact declare integer a local variable, so it needs 4 bytes for that. So that's where we're seeing, or why we're seeing that push. From there, that local variable, so we move into EBP plus local 8, a value of hex 0. So that's initializing that local variable a into or with a value of 0. And now we can get into our calling conventions. So as I said, you'll see a push 4, push 3, push 2, push 1. We're going to see each of these conventions push from the last argument to the first before the call to the function, and then depending on the convention, the appropriate cleanup. So with a standard call, we don't see the caller doing the cleanup. So after the function returns, because it is returning a value that's typically returned in the EAX register, that's moved into our local variable. EAX is then zeroed out. We have the epilogue, and that we take our stack pointer and we restore it by moving into ESP, EBP, and we restore EBP, and then we return. And so now we have what's typically called the epilogue of the function. So EAX, return value of 0. We see return 0 in our function here, and the program's ready to return. So what does this look like then inside of the function? Well, if we go to that function, as you can about imagine, we see again the setup of the stack frame with the prologue. So we push EBP, move into EBP, ESP. We then move our parameters into these registers in order to do the addition, because that's all the original function was doing. It's simply returning the value of those arguments added together, so A plus B plus C plus D. So we're just seeing that done through a series of instructions here. So as you now see with many popular disassemblers, decompilers, instead of seeing the raw offsets relative to EBP, remember EBP is a pointer to the base of the stack frame, then they use parameters, they use labels that make it a little bit easier to digest. I want to show you the raw offsets here. So one of the easiest ways that I've seen to do this, I imagine there is an easier way, I just couldn't think of it, was to right-click clear code bytes and then to go ahead and disassemble. So now you can see that those param variables have been removed, and we can just see the raw offsets. So as we're building a stack frame for a function, we're pushing on our arguments, then we're calling the function. So we push the arguments on. As we push the arguments on, the stack grows from a higher to a lower address. We then call the function that pushes the return address onto the stack. We enter the stack, we push EBP before we move into EBP ESP. So now that we're in the function, in order to reference those arguments, we have to go down the stack. So we have to be at a higher offset, because remember, those were the first things pushed onto the stack. So they're at a higher address. EBP points to the top of the stack once we get into the function. So therefore, we have to add positive offsets to EBP in order to get to those arguments. Those arguments were pushed on in increments of 4 bytes, even if the argument itself was not a 4-byte value. So let's say we pushed a char or a short. It would still push in increments of 4 in order to maintain the alignment of our stack. So that's what you can see here by just removing those variables, is that we have addition to positive offsets to get to those arguments. Now, if we were looking to access a local variable, so something below our stack frame, then we would have to go lower down the stack, actually higher on the stack, but to a lower address. So then you would see EBP minus and then the offset relative in order to get that local variable. So anyways, now you can see those arguments are accessed relative to EBP. The value, that memory address is dereferenced, that's moved into the register, and then we just continue to add those arguments to EAX, which works out great because then when the function is done, it was going to return the value in EAX. It's already done that. Now we simply pop EBP to restore the previous stack frame, and with this calling convention, we see the ret hex 10. So again, if we think about the arguments that we're pushing onto the stack, we pushed on 4 arguments, and each one happened to be 4 bytes. So if we open up a calculator and say 4 plus 4 plus 4 plus 4, you can see we get the result of hex 10, which is why we are ret hex 10. So what that is doing then is it is grabbing the return address that's currently on top of the stack after our pop EBP. It's grabbing that return address, and then it's also adding to ESP hex 10. That way when this function returns, let's go back to where it was called. When this function returns, we can use the result, the return value in EAX, and nothing else has to be done. The caller is not responsible for any further cleanup. Now let's look at C declaration, which is, I believe, one of the most common calling conventions to use amongst C compilers. We have very similar setup here, and that we have the beginning of our stack frame, much like we saw and already talked about, the creation of our local variable. We push from the last argument to the first, so push 4, 3, 2, 1. We call our function, and now you'll notice that after the function, there is an add to ESP 10 hex, right? Since we pushed onto the stack, that decremented our stack pointer 4 bytes with each push, we now have to recover that stack space. So that's where the add ESP hex 10 comes into play. Inside of the function then, everything will look pretty much the same. We have the same parameters, doing the same addition, returning an EAX. We get to the epilogue, we restore EBP, but now we have a regular ret. So we just are grabbing the return address off the top of the stack before we go back to that function. Okay, so that was the difference there. The caller is responsible for cleaning the stack. All right, finally, we have our fast call. And if you'll recall, fast call is using or favoring some registers instead of pushing or providing all of the arguments via the stack. Now, I said this was a potential performance benefit. That is, the CPU has direct access to those registers, and so it is very quick. There's a higher performance in obtaining values in a register versus having to go out and obtain that value from memory, from random access memory or primary system memory. And that's what happens when we are storing variables on the stack. So here we have push 4, push 3. So the last two arguments, in this case, because there was only 4 arguments total, and the first 2 arguments then are moved. So the second argument is moved into EDX, and the first argument is moved into ECX. And so that is the calling convention there. Now, with this convention, as you can see, it is also the responsibility then of the callee in order to clean up the stack, because we don't see after our function, we don't see a add to ESP in order to clean up at least 8 bytes from these 2 pushes. So in this function then, you'll notice at the end of this function, we have a ret hex 8, right? 4 bytes for each push. That is where 8 bytes comes from. You'll also notice that the prologue is a little bit different, and that we push EBP, move EBP, ESP, but then we sub from ESP hex 8. So this compiler decided that in order to support this calling convention, that there needs to be 8 bytes of local stack space for this particular function. So now we begin with moving into EBP plus local C and moving into EBP plus local 8, these 2 parameters, before we finally begin to summarize all of the arguments in order to return. So much like the previous, I'm just going to clear this real quick and disassemble. And now you can see that with these local variables, it's EBP plus a negative hex 8 and EBP plus a negative hex 4, right? Because local variables, we created space on the stack after we created the base, the stack pointer, the base of our stack frame. So in order to access those relative to EBP, we have to subtract. So it would appear then that our arguments for param1, param2 in our registers, ECX and EDX, are still moved into local variables before finally they are moved into ECX, and then you'll see the process of adding those together using those local variables and the arguments. That means then, when we get to the end, that this ret 8 hex is for the calling convention, is for the arguments, because when we move into ESP EBP, that essentially is clearing the stack pointer in the local stack space here. Remember that when we base the frame as part of the prologue, we then subtracted ESP. So restoring ESP to our base frame pointer essentially clears, at least it takes the stack pointer and resets it to where the function was at the beginning. So it accounts for any changes to ESP throughout the function. So for example, the sub ESP hex 8. You'll also notice, of course, that when it does this, any content in this memory and these local variables gets left there. Okay, and that's just a real brief introduction to 3 calling conventions commonly used by the compilers. As I mentioned at the beginning of this introduction, it is typically you don't define the calling convention, or when you don't define it anyway, it's up to the compiler to determine. It typically chooses cdecl, but again, the compiler can choose different conventions based off of just what determination it makes for performance reasons or maybe other options that you've provided to that compiler. As you can see here, you can also define the convention that you want. And the largest impact this will have, particularly for reverse engineering, is just being able to recognize the convention and then understand how the arguments are being passed into your functions. That way, as you're reversing a flow of a program, you're looking at those arguments, you can understand the values being passed into them to build that understanding of what that function is doing. So, hope you enjoyed the video, and I look forward to talking to you all in the next one. Thanks.